All right, so without using any graphing calculators, we complete this packet. We are going to do just a rough graph and state the domain and the range. Make sure that all earbuds are out, all cell phones are put away. All right, so let's think about what we can plug in here and if there's any restrictions. Knowing that it is an x squared, we know that whether it's a positive or whether it's a negative value that is inputted in for x, will receive the exact same output. So let's start with 0. So let's plug in 0. We know 0 squared is 0 and 0 minus 2 is negative 2. And you are just watching, you are not graphing this because you have the homework in front of you, or if you're present with me, these are different numbers. Whether I plug in a 1 or a negative 1, I'm going to get the same result here. So 1 squared is 1 and 1 minus 2 is negative 1. Same thing, negative 1 squared we can see is 1, 1 minus 2 is negative 1. So I'm going to go over 1 and down 1, and I'm going to go over 1 and down 1 as so. And let's just do 2 more. 2 squared is 4, 4 minus 2 is 2, and the same thing, negative 2 squared is 4, and 4 minus 2 is 2. So I'm going to go over 2 and up 2, over 2 and up 2, and we have a rough graph of what this looks like. Please turn to the person next to you. What are different ways that we could represent the domain and the range? Nothing on your paper, just verbalize and go. How could we represent the domain and the range? I'm going to give you 10 seconds. Begin. All right, so for this right now, we can see that we are not restricted what we plug in for x. So when we think about the domain of function f is equal to all real numbers. Is there another way we could represent it? Yes, it's negative infinity to positive. So right now you are just taking notes. This is different than what's in front of you. This is different than what's in front of you. This is just taking notes. You can just take out a piece of paper right now. Okay, so we have two different ways we could represent this. Either this is interval notation. Right here, we talked about this as being a different way to represent a different way to represent our domain and range. Now the range for function f, it goes as low as negative 2. All y values such that y is greater than or equal to negative 2. In interval notation, we would include the negative 2 and in anything greater. So I would like to see you write down both when you do your homework. Once again, this is different than what you have in front of you if you came in early and picked up a packet. These are two different ways to represent the correct answers. Let's go over here and look at example number 2. In example number 2, remember that inside of here, as we are only working with real numbers, this value can be as low as 0. So if I take x plus 3 and I set it equal to 0, I get an answer of negative 3. So I'm going to go all the way over to negative 3. When I input negative 3, I get an output of 0. Why? Because negative 3 plus 3 is 0, and the square root of 0 is 0. Now, as I move to the right here, I'm going to plug in negative 2. Negative 2 plus 3 is 1, and the square root of 1 is 1. I could plug in negative 1, but we're going to see that's not a pretty answer. Negative 1 plus 3 is 2, and the square root of 2 is irrational. The same thing, I could plug in 0, and I get the square root of 3, but when I plug in 1, 1 plus 3 is 4, and the square root of 4 is 2. We get a general idea of here of what this looks like as a square root function. So the domain of function g and the range of function g. All real x values such that x is greater than or equal to negative 3. And for the range, we have all y such that y is greater than or equal to 0. Now, if we wanted to change that up and write that in interval notation, we could do as such. Negative 3 greater than or equal, negative 3 to the right and 0 to the right. It's important that we are specific with how we do this. This is a bracket at negative 3 and 0 because we're including those in their domain and range specifically. All right. I would like you on your own separate piece of paper to try right now number 3. Try number 3 that I have here, not your number 3 that's on your paper. So if you have the back side of the packet, if you pick that up, or you have your own piece of paper, I want you to try this one. I'm going to press pause. So how are we going to go about doing this? Well, let's look at our values. I'm going to just start with 0. If I plug in 0, 0 cubed is 0, and 0 times negative 2 is 0. Let's try a 1. I plug in 1, 1 cubed is 1, that means 1 times 1 times 1, and 1 times negative 2 is negative 2, so I'm going to go over 1 and down 2. Let's try 2. If I go over to 2, 2 cubed is 8. 8 times negative 2 is negative 16. So I know I have to go way off the graph here, but we get a general idea it's going down in this direction. And now let's take a look and see what it looks like as we go to the left. Let's try negative 1. Now be careful, negative 1 cubed would be negative 1, and negative 1 times negative 2 is 2. Same thing here, as I go to negative 2, I'm going to get a positive 16. So I'm going to go way up here. Here is 11, it's going to be somewhere way up here, and this is our general shape. I would like you right now, giving you a time constraint of 20 seconds, to show me 2 different ways to write the domain and the range. 2 different ways to write the domain and range of this function. The domain, we're not limited what we can plug into this function, so it is all real numbers. We can also rewrite it as negative infinity to positive. The range for this function, again, is all real numbers and can be represented in the same way. All right, we're going to speed this up here. Here is your 4th example. I'm going to press pause. I would like you to graph this. You have 1 minute to do a rough graph of what this looks like. No technology. And if you're wondering, how do we go about graphing this? I'm literally going to enter in points here. So I'm going to enter in the first point of x equals 0. 0 squared is 0. 0 plus 2 is 2. So I'm at 0 and 1/2. I'm going to go to 1. 1 squared is 1. 1 plus 2 is 3. So I'm going to go over 1 and up a third. And watch, if we do negative 1, we get the same result, because negative 1 squared is 1 and 1 plus 2 is 3. So I can see that these 2 results will be the same even if we have a positive negative of the same number. So 1/3 here, 1/3 here. Let's try it 2. 2 squared is 4. Again, sorry, 2 squared is 4. 4 plus 2 is 6. So we can see that it's going up as high as 1/2, and then it's going to get closer and closer on both sides to the x-axis. So when we look at the shape, it goes up just a little bit and then it goes back down, right? If we folded along the y-axis, it would reflect on the left and on the right. With that being said, it goes up as high as 0.5. So it goes up as high as 0.5. A little bit trickier. Okay, with people at your groups, please go ahead and identify the domain and range of this function. I should hear talking within every group. Okay, so for this function, the domain, I can plug in any value I want. I'm not limited. So this is going to be all real numbers, or I could write it like this. Now the range is different. The range is different. So the range approaches 0 as it moves to the left and to the right. There is a horizontal axis here. It's never actually going to touch 0. So the range is going to be greater than 0, y's are greater than 0, and less than or equal to 1/2. Another way to write it in interval notation is we're going to go from 0 all the way up to 1/2, but we are going to include 1/2. There's actually a point where a y value is equal to 1/2. For these 2 examples, determine whether the graph shown is a graph of a function. Now, if it is a function, classify if it is 1-to-1. So is this a function? How do you know? And if it is a function, is it also 1-to-1? I'm going to press pause. Please turn to those around you. If you're by yourself, if you're most comfortable, you can put it into words on paper. All right, so to be a function, it means that every x is going to map onto a maximum of 1y. So I can use the vertical line test, and I can see that this does satisfy the vertical line test. So based on the vertical line test, this is in fact a function. Now, is it a 1-to-1 function, which is a specialized type of function? We talked about this on Friday. This is not 1-to-1, because as we can see here, I have this value that maps onto a y. Please don't talk when I'm going over this. This value of x maps onto this y value, and as does this value of x. So I can see that to be 1 to 1, every x value maps onto a unique y value. So no other x value would map onto this y value, but in fact we do have more than one. Same thing here. If I switch up the color so you can see it, and I switch here to, let's go with the yellow, we can see that at -3 it maps onto 1, and I can also see that right about here at 2.8 it maps onto 1. So it is a function, but it's not a specific one-to-one function. And we'll learn later on why one-to-one functions are important. If a function is one-to-one, it means it can have an inverse. Let's look over here. Is this an example of a function, yes or no? Nope, does not pass the vertical line test. Okay, let's jump down below and we're going to talk about what you learned in 8th and 9th grade. So, how do we identify algebraically, no calculators included, how do we identify the x and y intercepts? So to identify the x-intercept, I'm going to make y equal to 0. So here I'm going to have 0 equals 9x minus 2. I'm going to add 2 to the opposite side, divide by 9, and I have 2/9 is the x. Now I need to write it properly. This here is my x-intercept. So 9/2, 0. Now I'm going to find the y-intercept, and the y-intercept, x is equal to 0. So y equals 9 times 0 minus 2. 9 times 0 is 0, and 0 minus 2 is -2. Write it as an ordered pair, 0, -2. Let's look real quick at example number 9 over here. Now, what you know right now, what you know about in this form, in factored form, I can easily identify the x-intercepts in this problem as being 4, 0, -1, 0, -2, 0, and 5, 0. It's pretty easy. Now, how do we identify the y-intercept? Just like we did in the previous example, x is equal to 0. So when I plug x into 0 here, I get 0 minus 4, well that's -4, and 0 plus 1 is 1, 0 plus 2 is 2, and 0 minus 5 is -5. 20 times 1 is 20, 20 times 2 is 40. So my y-intercept is 0, 40. This is my y-intercept. These are my x-intercepts. Let's look over at example number 8. I guess I didn't do these in order. In example number 8, same concept. How do I identify the x-intercepts? I let y equal 0. I let y equal 0. So 0 equals 2x squared minus 7x minus 4. And we learned in 8th and 9th grade and at the beginning of this year multiple ways you can take a quadratic function and you can solve it. You can always use the quadratic formula. You absolutely have to have that memorized. Quadratic formula always works. X equals -b plus or minus b squared minus 4ac all over 2a. That works every single time. Sometimes you can factor and solve, and when you can do that, for me, I think that's the fastest way. I'm going to try that. 2 times -4 is -8. Are there two values that multiply to give us -8 and combine to give us -7? That would be, in fact, a -8 and a +1. So remember, if it's not factorable, it doesn't mean we can't solve it. It just means then we'd have to use the quadratic formula. So 0 equals 2x squared minus 4. And in the middle here, I'm going to drop down the two values I was able to determine. And now I'm going to go about factoring here. So I can factor out a 2x, and I'm left with x minus 4. I rewrite the x minus 4. What times x is 1x, 1. And 1 times -4 is -4. They both contain an x minus 4. In the front is a 2x, and the back is a +1. And now I'm going to set each of these equal to 0, and I'm going to solve. So x minus 4 equals 0, and 2x plus 1 equals 0. And I would have an answers of x equals 4, so 4, 0 is 1. I subtract 1 to the opposite side. I divide by 2, and I'd have another of -1/2, 0. These are the two x-intercepts. In this form, you learned this in 8th and 9th grade. In this form, ax squared plus bx plus c, your y-intercept can easily be found by looking at the c value. Your y-intercept in this form is 0, -4. If you forgot that, remember we plug in 0 for the opposite variable, which is x. So 0 squared is 0 times 2 is 0, -7 times 0 is 0, and that's how we end up with that -4. Okay, are you ready? It is a race, so we're looking at this last example before we go on to the next set. Please figure out the x and y intercepts. We are only working with real numbers right now. Keep All right, so let's figure out what the x-intercept is. So for the x-intercept, I'm plugging in 0 in for y, and I'm solving. So 0 goes in for g of x. And the first thing I do is I subtract 1 to the opposite side. I take the square root. I'm going to have two answers, a plus or minus, but we can't take the square root of a negative, so it comes outside as an I, and right away I know I'm done because I'm only working with real numbers. So there's no y-intercept. There's no y-intercept for this particular problem. Now hold up here. I disagree with that. So hold on here. I meant to say x-intercept. There's no x-intercept, and I totally agree with that. Sorry, there's no x-intercept. Now let's figure out the y-intercept. Let's figure out the y-intercept. So I'm going to plug in 0 for x. Plugging in 0 for x, I get 0 squared is 0. 0 plus 1 is 1, and I have a y-intercept of 1. So 0, 1 is the y-intercept, and there is no x-intercept. Let's go on to our next concept. All right. So in this problem, we want to be able to state the intervals that are increasing, decreasing, and constant. All things that we learned early on this year. So from left to right, we are only going to think of this in terms of x values. So in terms of x values, it is increasing on this interval right here. From left to right, it is increasing. So it comes from the far left, and it continues to increase until you get to an x value of -4. Now at -4, it's neither increasing or decreasing. It increases up to that point, and at this point, -4, x equals -4, it is not increasing or decreasing. Remember, for increasing, decreasing, or constant, we only ever use parentheses to describe those. Where is it decreasing? So after it leaves the point -4, it decreases as it moves to the right. So a lot of students want to put a negative infinity here. That would describe the x values of it going down in terms of, that would describe the y values. In terms of x values, as it moves to the right, positive infinity, it continues to decrease. Now this function is neither increasing or decreasing, it is constant. Now where is it constant? The entire way it is constant. Lastly, we have this polynomial function. Let's go from left to right. So we have increase and we have decrease. I see no constant. So on this section right here, it is going down from left to right. So it comes from the far left in terms of x values. It decreases until it gets to an x value of -6. Now from -6 all the way to an x value of -2, it is increasing. And then after it leaves -2, it goes back to decreasing as it moves to the right. Right, so in the next part, we are going to look at a graph. So the graph's already going to be provided to us, and we want to identify what are the relative or local points. That's both your maximums and your minimums. And what are the absolute or global points? Again, that's going to be your maximum or minimums. So let me just give you a really simple graph here that you can look at. Very, very, very simple. If I gave you this odd shape here, let's first start talking about absolute or global. If an absolute, so those are interchangeable terms, if an absolute maximum occurs, it means there is one and only one point on a graph. There can never be two. There's one and only one point on a graph that stands out as the absolute highest point, the highest y value. And likewise, if an absolute or global minimum occurs, it means there's one and only one point that stands out as having the lowest y value. There can only ever be one absolute maximum and one absolute minimum, and sometimes they just don't exist. Now, relative, there can be more than one relative or local maximum or minimum, and those are turning points. This is a turning point. It means when it goes from decreasing to increasing or increasing to decreasing, and it creates a high or a low point. It just doesn't stand out as the highest or the lowest. So if we look at this graph right now, what does this tell us? What does this arrow tell us about either one of these? Turn to your partner, go. What does it tell us? This means what? Is it ever going to stop going up? It's never going to stop going up. If this never stops going up, will there ever be one point that stands out as the highest? No, so I know there is no absolute, and maybe called global, depending on who writes your test, maximum. All right, but is there an absolute or global minimum? Do you see this point here? It's not an arrow. Does everybody see this point? I just stopped it so we could have an absolute. This stands out as my absolute. Again, it may be called an absolute minimum, or it may be called a global minimum, but it is the lowest y value. These are called turning points. It's literally when you turn from going to decreasing to increasing, or increasing to decreasing. So this is still a low point. It may be called a relative or a local. I'm going to abbreviate a relative or a local minimum, and this would be a relative or a local maximum. It's a turning point. This would be a relative or a local min, and this would be a relative or a local maximum. So let's take a look right now. Okay, tell me what you know about this. This would be, hold on here, we are on here. This is going to be the point negative 5, 3. This is the point 0, 6. This is the point 2, 0. Okay, what do you know about just this graph in terms of relative and absolute maximum mins? Turn to your partner. What could you come up with in 20 seconds? Go. A point cannot be a relative and an absolute maximum min. It's either one or the other. Does one point stand out for a y value as being the highest in this particular function? This does, right? This stands out as the highest. 3 is the highest y value. So this is called an absolute or a global maximum. Is there an absolute or global minimum in this problem? No, because these arrows say keep going down. You cannot just pinpoint one. This is going to go down to the left and down to the right. It's not going to stop. So there's not one point that we can identify as the lowest. There is no relative. There is no relative or local max or min. Let's look at this problem. Turning to your partner, I'm going to press pause. Again, I want you to identify those local and absolute max and mins with your partner. All right, so for this problem, this tells me there is no absolute or global maximum. This tells me there is no absolute or global minimum. Why? Because it continues to go up as it goes to the right, so it's never going to stop. We can't just pinpoint one point as being the highest or the lowest. These are going to be referred to as local or relative maximum, and this is a local or relative minimum. Okay, a little bit trickier. To your partner, you have 20 seconds for this example. A really tricky one. But you know what? There is no absolute or global max. There is no absolute or global minimum. And in fact, there's no turning point here. Turning point means where it goes from going up to going down. So there's no increase and then decrease. So there is no, if there's no turning point, that also means in this particular problem, there is no relative or local max or min. So there's none of all of them. Okay, let's go on to this one right here. Think of this as a quiz right now. On your own, you can do it in your head, you can do it on paper. Go. There is an absolute or global maximum at 0, 4. There is no one point that stands out as the lowest. These get closer and closer to the y-axis. They never touch it. So this means it continues to go down, but it's never actually going to touch the y-axis or the x-axis. It's never going to equal y equals 0. So it's going to continue to go down, but it never actually touches that. So there's not going to be a global or absolute minimum, and there's no turning point because what is an absolute cannot be a local. All right, so right now we are going to use this parent function that's provided to us, and we're going to rewrite it in a translated form. So I have, and we're going to rewrite it here. Whoops, sorry, it should have been the word down. Okay, so when we rewrite this, we're going to take this original function, and now we're going to shift it down 4 units. Remember that any vertical shift goes behind the function, and it's going to be just what you think. So down 4 will be -4. If it was up 4, it would be up 4. Positive 4. Horizontal shifts will go inside in this case, and it's going to be just opposite of what you think. So 4 units to the left, instead of saying x -4, which would make sense, it's going to be x + 4. Here's something I do want you to write down. Please write down for an x, you're going to want to write this down somewhere on your notes. X reflection. Again, reflection across the x-axis is how I should have stated that. We have y equals negative f of x, and for a y-axis reflection, This is freshman level, but it's very possible you forgot this. It's y equals f of negative x. Okay, so when we reflect across the x-axis, we're doing the exact same concept. When we're reflecting across the x-axis, I'm going to take this function, and all I'm going to do is slap a negative sign in front. That's all I did. Slap a negative sign in front of it. Now, when I reflect across the y-axis, I'm going to go to wherever there was an x value. So here's where the x value was, and I'm going to put a negative x inside. Hopefully you remember this freshman year. Okay, let's go down here. So I have g of x. I'm going to reflect it across the x-axis. So this negative sign is going to go in front, and then when I distribute it to everything behind, no, we can't distribute through an absolute value if you're wondering why I didn't do that up above. When I distribute this, I get, this is going to be the translated function, negative x squared minus 3x plus 2. When I take this function and reflect it about the y-axis, remember I'm going to replace every x with a negative x. So the translated function here, what would negative x squared just give us? X squared, because a negative squared is still going to be a positive. Here I'm going to replace the x with a negative x. So I have g of x equals x squared, and if you wanted to put a negative one there, you can, but negative x squared just gives us x squared, and 3 times negative x is a negative 3x.